So binding's favorable, but what's happening with the entropic term? So what's going on in this figure here is we have the protein and the ligand separate. They have 3 degrees of translational freedom each, meaning X, Y, and Z direction. They can move through space. The protein can move through space, and the ligand can move through space. They also have rotational degrees of freedom about all of those axes. So again, the protein can spin in space, the ligand can spin in space. And then also along the ligand itself, at each of these like backbone spots, there could be some additional rotational conformations going on. So these are changes in entropy upon the freezing out of motions of the small molecule. So when these two things bind, we lose a whole bunch of entropic sort of freedom, right? This is much more entropically favorable than once they're actually complex together. So there's the loss of translational entropy for a small molecule. So we have entropy changes and contributions to delta G. The delta G is very positive here, okay? So it's sort of bad for delta G. The entropy is going down. This is sort of confusing because it's positive, but this is sort of the difference in entropy. But we're losing entropy. It's becoming more negative for entropy, but the contribution to delta G then, since we subtracted, is it's more positive. Okay? When you lose rotational entropy, what is that doing to impact free energy? When you lose the bond rotations, what is that doing? Okay. So how do you think we sort of overcome, from a free energy standpoint, the fact that it's really entropically unfavorable to bind these two things together? What else is involved that makes entropy favorable? Water. Perfect. Water molecules are trapped inside the binding site. There's hydrophobic residues trapping some water molecules that can't really make a favorable interaction but are held there. And when the drug comes in and binds, it displaces all of the water molecules. And the freed water molecules have a bunch of increased entropy, such that the net can still be an entropically favorable situation. Okay? But again, you can kind of only exploit this so much, right? At some point, like I said, specificity and affinity are in competition with each other. So we can't just put as many hydrophobic residues as we want on forever. It won't work.